The purpose of this presentation is to review what you know about linear elastic finite element analysis. So, start with what is FEA? Well, it's a method of simulating the behaviour of objects, and it can be used for calculating stress, strain, deformation in structures when they're subjected to static or pseudo-static loads. So that can include things like metal forming problems, extrusion, pressing processes, and in fact the all display down here shows the process of forming a V-band section as we go through the 6 rollers. So we start with a flat strip up here that's gone through the first pass, been bent slightly, and then we go down to the 6th pass there where you've fully created the V section of the V-band for a V-band clamp. You can also use FEA to simulate the response of structures subjected to dynamic loads, so you can extract natural frequencies and mode shapes and look at frequency response. You can look at thermal effects or calculate the temperature distribution or the effect that temperature distribution has on the structure. You can look at electromagnetic fields, and you can even use FEA to simulate the flow of groundwater, which is probably going to be important when people are looking at fracking and the effect it might have on drinking water. Here's another example of the use of finite element analysis. So this was a crankshaft for a V10 prototype engine, and in the form it was originally the prototype was produced, it was actually made from 21 parts all pressed together. So we've got these separate discs and these separate shafts, and they're all pressed together. Now the difficulty with that is it's virtually impossible to actually manufacture that using pressure operations to the tons as it requires to run the engine at any sort of reasonable speed. So the question was, could that be made from a single casting, and stress analysis was required to investigate the final machined shape. And one of the problems that was very quickly identified was that the sharp internal corners that are produced during the pressing operation don't create stress razors, but if you try and then make those same sharp internal corners from a single piece of material, then you will get very high stress razors, and they needed to be eliminated. So how does FEA work? Well, to start with, we need to know what the fundamental relationship is between whatever our input is and our output, and we need that in the form of an equation. So we need to, if we've got a load applied to a structure, we need to know what the response is. We need an equation which gives us that response. Now that equation describes what happens at a point or within an infinitesimal cube. So for elastic analysis, we know that the force displacement relationship is determined by Hooke's law, and that works in the material at a single point within the material. Now for most real objects, this load response relationship, whilst we can define it easily for a single point of the material, it's virtually impossible, and in many cases it is impossible to work out what that is for the whole structure. So this is where FEA comes in. So the finite element approach is to divide the structure into lots of small parts. These are finite sized elements. Within each element, the load response equation is approximated by the load response equation for the infinitesimal cube, or what's happening at a point. We then connect lots of these elements together, and the response in one element becomes the load on the neighbouring element. We end up with a sort of knock-on effect, and that gives us a response of the whole structure. Now you're going to need many elements to give you a decent result, so within each element there'll be a number of equations, so you'll end up with lots and lots of equations, and That means you're going to need a computer to solve all those equations, which is where the finite element analysis packages come in. Now that leads on to a fairly obvious question, which is how good are FEA results? Well, we need to recognise that there are two types of approximation in a finite element model. The first approximation is an approximation which applies to any simulation. No simulation is going to give you exactly the same response as the real object, and that's because real objects are simply just too complex. So in any simulation, whether it's a finite element analysis or not, we're going to be approximating the geometry of the object and also the things like the material properties of the object, and we're going to be approximating the object's interaction with its surroundings. The second approximation that we get in finite element analysis is the approximation we've just described in the previous slide, which is that what's happening in the element is approximated, the load response equation is approximated from what happens in the infinitesimal element. So that equation is only actually true for an infinitesimal element, but we then say that our finite element is small enough for that equation to give us a reasonable approximation. Now, that means that if you've only got a few elements in your model, then that's going to be a crude approximation of the true behaviour of the model, and to get a better approximation we need to use more elements. And if we use an infinite number of elements, then we will get the true response of the model. Remember, this is of the model. The model's created up here, and that in itself is an approximation. Now, we need to understand something about the theory of finite element analysis in this module, and within this module I'm going to use the principle of minimum potential energy to derive the theory. I could use the principle of virtual work, but I think that the principle of minimum potential energy gives us a better understanding. So to help explain the principle of minimum potential energy, I'm going to use this little example on the right hand side here, where we've got a mass hanging from a spring. And if we deal with the mass individually, we forget about the fact that it's hanging on a spring. We've got the mass and it's some distance above some surface, so it's got potential energy. If we then reduce the distance it is above a surface, then we're going to reduce the potential energy. So this is a force potential energy that's being reduced. We're changing the force potential energy, we're reducing it, and we're reducing it by changing the distance we are above the surface. Doesn't matter where that surface is, the change is still going to be the same, but we're changing the distance by that amount, and that gives us a change in force potential energy. And you'll see here that if that's the force and that's the distance the force is moved, then what we've effectively got is the work done, but it's minus work done. So the change in force potential energy is negative work done. If we then look at the spring here, the spring is being extended. Well, if we extend the spring, we change its elastic potential energy. In fact, if we compress a spring, we change its elastic potential energy as well. And the equation for that is half spring stiffness times change in length squared, which we've got down here. So we've got the change in elastic potential energy, half spring stiffness times change in length squared. In this case, we're extending the spring. And I'll use the symbol uppercase U to indicate the change in elastic potential energy. So then the total change in potential energy is going to be our change in elastic potential energy plus our change in force potential energy, or minus work done. Now, just to make that equation a little bit less cumbersome, I'm going to use lowercase u to define the change in length or position, and I'm going to use F in place of mg for the force, and that helps to generalise the equation a little bit as well. So we've now got this equation for the change in potential energy, half spring stiffness times the change in length squared minus force times distance, and we can also write that simply as the change in potential energy, so I'll use uppercase V for the total change in potential energy, equals change in elastic potential energy minus work done. If we put some numbers into those equations and plot them out, plot the results out, then we'll get a graph that looks something like this. Here's the work done increasing linearly. Here's the change in elastic potential energy going up because it's squared. And remember that we take the work done off the elastic potential energy to give us the total change potential energy, and that forms this curve down here, which clearly has a minimum. Now, if we think about this in terms of what's happening to the potential energy, if we go either side of that point, then we are going to be increasing the potential energy. So at this point here, we've got minimum potential energy. Now, if the potential energy is going to increase, then that means the object's going to want to stay at that point there. That's going to be the point it wants to be at, where we've got that minimum potential energy. And in actual fact, you can prove that that's the case for the spring mass system, where the spring force balances the force due to the mass, and I'll leave you to work that out. Extending that little relationship further, we can say that of all the possible displacements that satisfy given boundary conditions, those that satisfy the equilibrium conditions make the potential energy assume a stationary value. For stable equilibrium, the potential energy is a minimum. Right, moving on to the simplest element, the one-dimensional linear element, and applying the principle of minimum potential energy to that element. Let's just run through the features of the element here. We've got two ends to the element. That's where we're defining the force applied and the displacement. So we've got a force and displacement at either end of the element. The element's got a length L, and because it's a one-dimensional element, it's got a cross-sectional area A. Because it's a linear element, any displacement we want anywhere between those 2 points is going to be a linear interpolation of the displacement at those 2 points. So to formulate the stiffness matrix for this element, we start off by looking at the strain energy. Now the strain energy at a point within a material is a half stress times strain. So if we want the total strain energy, we need to integrate that over the volume. So we're integrating over the volume of the element. Well, for this one-dimensional linear element, if we think about an elemental volume there, then that elemental volume has got a fixed cross-sectional area, and we can change, therefore, multiply that fixed cross-sectional area by an elemental length, and that gives us a replacement for the small amount of volume. So we've now got A times a small amount of length dx. It's a one-dimensional problem, so stress is equal to Young's modulus times strain, and because we are only defining the displacements at either end of the element, the strain can simply be defined as the difference between those two displacements, which will give us a change in length divided by the original length L. So if we feed this information back into that equation there, we will get a new equation for the strain energy. So that's this equation here. Let's just run through what we've got there. So we've got Young's modulus times strain, so that's the stress term. Then we've got the strain term, change in length divided by original length. Then we've got A dx in place of d vol, and we need to be integrating over the length now. And that will give us the same effect as integrating over the volume, because we've got the A dx as on the end there. Now all these terms here are constants with respect to position. Yeah, the Young's modulus doesn't change over the length, the area doesn't change over the length. These displacements are only defined at the ends, and the length is a constant for the element. So all those can come out of the integral. So we're left with this as the integral. We're just integrating 1 over the length. And if you integrate 1 over the length, you get length. So that will then cancel the squared term there, and we end up with this fairly simple equation for the strain energy in the element. Okay, so continuing from the previous slide, we've got this equation for the strain energy. We now need an equation for the work done. So looking at the diagram again, we've got a force travelling a distance. That gives us work done at node I, Fi times Ui, and then the same thing at the right end, we've got Fj times Uj. Simply need to add those two together to give us the total work done. That then allows us to write down the potential energy equation. So we've got the strain energy term there minus the work done term. Now, to work out the minimum potential energy, obviously we're going to have to differentiate this, and we're differentiating it with respect to the two displacements, so we need two separate differentiations carrying out. So here's the first one, differentiating the potential energy with respect to Ui. So we've got differentiate the bracket as a whole, cancels the 2 there, differentiate what's inside the bracket, it's going to give us a minus sign, so we get minus that term, and then plus that times that, and then the work done term, differentiating that with respect to Ui, there's only that bit that needs differentiating, just gives us Fi, and got the minus sign there, and that has to be equal to 0 for equilibrium. Differentiating with respect to Uj gives us this equation here, so again that has to be equal to 0 for equilibrium. So we've now got two equations for that have to be equal to 0 for equilibrium, and those two equations have to be equal to 0 at the same time. They are a pair of simultaneous equations, and we can express those two equations in a single matrix expression we've got here. If you multiply out the top row of that matrix expression, you will get the first equation, and if you multiply out the bottom row, you will get the second equation. And that is our stiffness matrix for the single one-dimensional linear element.